Hello and welcome all. Today we are going to discuss about why the inductor current is lagging behind the inductor voltage. This is the waveform of the inductor voltage, inductor current and input voltage. Look at this. This is the input voltage. This is a sinusoidal voltage of 50 Hertz. So 50 Hertz means the time will be 1 by 50 is 200 millisecond. The maximum peak will be at 50 millisecond. 1 by 4th peak will be at 50 millisecond. And the input voltage is, if we say maximum input voltage is 10 volt, that means at 50 millisecond the input voltage reaches 10 volt. Now what will be the current waveform and why we are saying that the input current, this is the input current, inductor current is lagging the input inductor voltage. What is the property of the inductor? The property of the inductor is that it will oppose anything that is going to change the energy of it. So when the input voltage is applied, the inductor, the self-inductance of the inductor will oppose this change by introducing the same amount of voltage, but it is in opposite direction. That means when it is at 50 millisecond, the input voltage is at maximum. So at that moment the inductor voltage is also at 10 volts, but the polarity will be opposite. Now we will look at why the inductor current is lagging behind the inductor voltage. Now to know that, we are turning this. Now this is the inductor voltage and this is the current. The inductor voltage is happening first and the inductor current is following. This is happening first and the inductor current is following. This is starting from 0 at maximum. After 50 milliseconds only the inductor current is starting in the same direction. How the current waveform will be look like this? In order to know that, we assume that we are applying an input voltage to this inductor. This is a 1 millihenry inductor and we are applying a sinusoidal voltage of peak voltage maximum 10 volt is applied to the inductor, and the inductor voltage is opposing the same. If plus 1 voltage is applied here, the polarity will be plus at this end. So in order to oppose this input voltage, and as we know that the inductor voltage is equal to the equation of the voltage of the inductor is L into I by dt. That means if we consider the inductance of the inductor as 1 millihenry, when the input voltage is going to rise and reach at 2 volt, when this input voltage reaches at 2 volt, the inductor voltage is also 2 volt to oppose the same. In order to have, when the input voltage is at 2 volt, the inductor voltage will be also at 2 volt but in the opposite direction. So the voltage, inductor voltage is VL is equal to L into di by dt, or we can say that when calculating the di by dt is equal to V by L. So V by L, V is 2 volt and inductor value is 1 millihenry. So the change in current should be, this is given by 2000 ampere per second. Now it is changing with a rate of 2000 ampere per second. If it is allowed to continue in the same state, in 1 second the current will be reduced from 2000 to 0. That is means the rate of change is 2000. But if we look at this point, when the input voltage is reached at this point, the inductor has to spend more energy. The inductor has to spend more energy to oppose this voltage. This is a low voltage and this is the input voltage is high. When the input voltage is become 10 volt, the inductor has to spend more energy to oppose it. So when the input voltage is 10 volt, di by dt is V by L, 10 by 10 into 1 into 10 raised to minus 3 is equal to 10,000 ampere per second. Now the rate of change is 10,000 ampere per second. That means it is changing so fast. Now we will look at this more closer. When the input voltage is at 2 volt, the change in current is 2000 milliampere per second. That means the change in current is, this is 1 millisecond. This is 1 millisecond. And the current has changed from 1 ampere to a less value in 1 millisecond. Because the energy required to oppose the input voltage is less. So it can maintain the same current, almost the same current. A very less amount of energy is wasted to oppose the inductor current. Now at this point means when the input voltage is high, the inductor has to spend more energy. Inductor has to spend more energy to oppose the input voltage. So in the same 1 millisecond, this is also 1 millisecond, this is also 1 millisecond, the change in current, the change in current is more, because it cannot able to maintain the same current. If it is less voltage, the current will be like this. But as more energy is spending by the inductor to oppose a high input voltage, the energy of the inductor reduces and it cannot able to maintain the same energy. So the current will be reduced. So when the input voltage is high, the rate of change at which the current decreasing is more. So at this point, when the input voltage is maximum, the rate of change of current is so high. In this point, the inductor has no more energy, almost no energy to continue in the same current. So the rate of change will be very high at this point. Now we will check the 2 points. When the input voltage is say 2 volt and the current say 1 ampere, the peak current is 1 ampere, inductor current is 1 ampere. That is when the input voltage is 2 volt and dt is the change in time, dt is 1 millisecond. If we take a small time 1 millisecond, by this time what is the change in energy, and so what will be the change in current. So if we consider the maximum current IL is 1 ampere, so for 1 millisecond the average current will be, if 1 ampere is the current is 1 ampere, for 1 millisecond we will take the average current. 1 ampere into 1 millisecond, 1 ampere into 1 millisecond is 1 milliampere. The average current is 1 milliampere. For 1 millisecond, an average current of 1 milliampere will be flown through the inductor. So, and the input voltage is to be opposed is 2 volt. This is the 2 volt. The inductor has to oppose this 2 volt. So the energy spent by the inductor is the voltage into current. This 1 milliampere of current has to possess 2 volt of energy to oppose the inductor, the input voltage of 2 volt. So 1 milliampere current into 2 volt, 2 milliwatt. Voltage into current is 2 volt into 1 milliamp is 2 milliwatt. In 1 second, only 2 milliwatt of energy is required to overcome the input voltage of 2 volts. When the input voltage is 2 volts, in 1 millisecond, the inductor has saved the energy in the form of flux. So it has to spend only 2 milliwatt of energy in 1 millisecond. So it is not much energy, so it can maintain almost the same current, only with a less change in current. So the rate of change at this point is very less. Now look at a point where the input voltage is 5 volt. The input voltage is 5 volt means the inductor has to spend more energy. 5 volt, it has to oppose 5 volts. So the current each electron has to spend more energy to oppose the input voltage. Now we will check when the input voltage is 5 volts and we are considering for 1 millisecond, and now the input current has changed from 1 milliampere to 0.7 milliampere. If we say that it is in these portions, the rate of change of current is not so big, it is very small. So when the input voltage is at 5 volt, the input current, if we say, is reduced to 0.75 ampere. 0.75 ampere or 750 milliampere. If this current flows for 1 millisecond, the average current will be 0.75 milliampere. The average current for 1 millisecond will be 0.75 milliampere. And the voltage to be opposed or overcome by the inductor is 5 volts. So the inductor has to spend an energy of 5 volts, and so each electron has to carry this voltage. The current flowing through the inductor is 0.75 milliampere, and each has to possess 5 volts. So the total energy required is 3.5 milliwatts. Earlier it was 2 milliwatts when the input voltage is 2. Now when the input voltage become 5 volts, the inductor has to spend more energy to overcome it. So the inductor spends more energy in overcoming that. So 3.5 milliwatt will have to be spent. Now the inductor has to spend more energy, that is 3.5 milliwatt. So change in energy in 1 millisecond is 3.5 milliwatt when the input voltage is 5 volts. But in earlier case, when the input voltage is 2 volts, the inductor has to spend only 2 milliwatt. When the input voltage reaches at maximum, the inductor cannot maintain the same current. That means each has to possess more energy, so the energy is more on each electron, so the inductor energy reducing, so it cannot maintain the same current. So the rate of change will be more at these points, and the rate of change is less at the when input voltage is less. Why the inductor current is increasing? Even if the inductor input voltage is decreasing, the inductor current is increasing. Why? If it is a resistive circuit instead of an inductive circuit, as the input voltage is decreasing, the current through will also be decreasing. But here, as the input voltage is decreasing, the current is increasing. Why? Because when at this point in the input voltage reaches maximum, the inductor current has reached zero. Inductor current has energy, and it is opposing the change in input current, and at these points the energy in the inductor is very less, so the current in the inductor reduces rapidly. Here it is not changing rapidly as the input voltage is low. No high energy is needed to overcome this. But in this point, as the input voltage is high and the energy in the inductor is at this point is very less, it is reducing very rapidly, and when the input voltage reaches at maximum, the inductor has no more energy. When the inductor has no more energy and the input voltage is high, energy required to oppose the input voltage is more, and in the inductor has no more energy is left, it can oppose it for a less time. So, and the input voltage is high, the rate of change is high at these points. But when the inductor current when the input voltage reaches at 0, the inductor does not want to oppose any voltage. At this point, the inductor does not want to oppose any voltage or any force, so it will remain there. If no voltage is applied at this point, the inductor current will continue like this. Why the inductor current is decreasing from here is that now we have applying an input voltage in opposite direction, so the inductor has to spend energy to oppose this voltage. So the inductor has opposing the voltage like this, so energy has to be spent. As this voltage, input voltage is very less, the energy at these points are very less, so the change in current will be very less. As the input voltage is increasing, more energy has to be spent, so the rate of change of current is increasing. That is why the current waveform will be look like this. If we turn it like this, now we can see that the inductor voltage is now we can see that the inductor current is lagging the inductor voltage by 90 degree. 90 degree means this is 360 degree, and this is 270, this is 180, this is 90. That means it is 180 and this is 90. This is lagged by 90. That is why the inductor current is lagging the inductor voltage.